My name is Emily Gorcenski. I'm a data scientist with Thoughtworks based out of Berlin, though you can probably tell from my accent that I'm American. And I'm here to talk about what I think is the next wave of data science and what's cool about it. But this talk is half historical, and I wanted to sort of call out Neil's talk this morning. And I like to spice things up. It's also late in the afternoon. We're all probably sleepy. So I have here 5 quid. I'm American. Am I allowed to say quid? 5 pounds. To anyone that can name, so Neil had the F-16 up there talking about old languages. If anyone, without using Wikipedia, can tell me what the F-16's flight control software was written in, what language it was written in, this 5 pounds is yours. And just shout it out at any point during the talk, and you can come collect your 5 pounds. There's a hint. The hint is that it was the same language that was used to write the UK's air traffic control system, and it actually may still not be retired, but it was scheduled to be retired only 2 years ago. So I'll let you think on that for a little bit of a brain teaser. I'm a data scientist, but data science is a fairly new field, and not a lot of people who work as data scientists are trained formally in data science because it's so novel. My background is in computational mathematics, and if you have a background in computational mathematics, before data science became a thing, you often worked in one of 2 domains. One is high-performance computing, or the other could be embedded real-time systems. So I actually worked as a control theory research engineer for almost a decade, and eventually realized that a lot of what I was doing became what's now known as data science. So the methods, the algorithms that I was using served as the foundation of what we have as modern data science. So I just started calling myself a data scientist instead of a controls engineer, and then magically got 25% more money. But I want to walk through a brief history of data science to tie in what's important, what's relevant about that domain, and where we are going from here. So another little brain teaser. Let's just sort of warm everyone up. See if you can figure out which of these came first. So I'm living in Germany. Naturally, we have to talk about David Hasselhoff. Was he born first? Rosalind Franklin discovered the double helix structure of DNA, or the genetic algorithm was invented. So I'll give you all a moment to think on that. And if anyone knows the answer of which came first, go ahead and shout it out. C. OK, C. All right. Yes, C is actually correct. Alan Turing conceived of the genetic algorithm in a paper in 1950, although the first implementation wasn't until 1954. David Hasselhoff was, of course, born in Baltimore in 1952, and Rosalind Franklin finalized her research on the double helix structure of DNA in 1953. So evolutionary computing is now almost 70 years old. Let's go a little bit more modern, a little bit more in vogue. Which is first, the deep learning neural network, the last people left the moon, or Led Zeppelin 4 is released? And this one is a little bit trickier. A. Kieran is good at this. Yes, deep learning was invented in 1971, the first implementation. It was an 8-layer polynomial neural network. Back then it was called the Group Methods of Data Handling. And that was in October 1971. And of course, only a couple of weeks later, Led Zeppelin 4, the seminal album, was released on Atlantic Records, and guitar shops have not been the same ever since. And then a year after that, the last people left the moon on Apollo 17. So the point of all of this exercise, is to realize that data science, as we know it, is not actually a new field. And it's built on technology and techniques that are actually quite old. Genetic algorithms, evolutionary methods, are 70 years old at this point, and they are still used today. We're still innovating on them today. The backpropagation algorithm was invented for control theory in 1960. It is still the sort of bread and butter of modern deep learning systems. Reinforcement learning, the first application was in 1972, and we're only now just starting to see the really cool benefits of reinforcement learning. And that's, well, it's what, 2019? So that's almost 50 years ago. Oracle's database, V1, 1978, and deep learning, the term, was invented over 30 years ago. So the things that we are finally starting to realize in data science were actually quite old. And what that has meant is that the theory and the understanding has outpaced our ability to implement it with technology. In 1994, this phenomenon was sort of observed. So this is, again, 25 years ago. This is not a particularly noteworthy paper. It's just the first one that I happened to find that addressed this problem explicitly, where these authors say that parameter estimation algorithms of a certain type for achieving a certain thing are all of general character, and they're well known for the traditional model structures used. They have typically been reinvented and rediscovered in the neural network literature and have been given different names there. This certainly has had an alienating effect on the traditional estimation communities. So what we have is this world wherein systems engineering has been doing all of the things that we're doing in the AI space and in the computer science world, and has been doing it for quite some time, but we've called it very different things. And the computer science world kind of rediscovered it, reinvented it, branched out, and developed in parallel for about 25 to 50 years, depending on how you look at it. And as we know, long-running feature branches are really annoying to merge. But we're getting to the point where we're going to have to sort of merge these concepts back together. So if we recognize that, much like in the IT industry, when the web took off, we started developing things in parallel and techniques separately from enterprise IT, and it's very painful for us to merge those techniques and those practices back into the IT space. The same is true in the data science world. But what I really want to talk about is physical computing, because it's problems that we're solving in data science today are things that are really fascinating and very important, things like computer vision, recommendation engines, chatbots. I think that's really fascinating, but I also think that that's a very small sliver of the potential of data science. In 2015, McKinsey did a study of the American marketplace, and they looked at what industry sectors had the highest and lowest relative levels of digitalization. What they found is that in some of these industries, such as agriculture and mining, healthcare, basic manufacturing, transportation, etc., are the lowest relative levels of digitalization. What's important about this is that this was 2015 that this study was published, and this was really before the this was really in the pre-IoT phase and before the data science revolution really took off. So if we were to redo the study now, that level of digitalization has shifted enormously, because now certain areas are really being able to use data science and data science capabilities, and even things that had pretty decent digital adoption at that point are now behind the curve. So yes, we have advanced manufacturing where we have mechatronics and computer-controlled machines, but those are not hooked up to the internet. We're not using the data on those devices in an effective way, and we can do more in that space. To give you a working example, the Boeing 787 Dreamliner, there's an estimate that it generates about 500 gigabytes per flight. There's around 550 airframes currently in service of this aircraft, which means that if those planes, each of them takes one flight per day, and most of them take more than one flight per day, but some of them are being maintained. If we assume that there's one flight per day, the Boeing 787 fleet generates about 227 terabytes of data daily, which is roughly about as much as YouTube generates in a given day. And that's just one airframe throughout the world. Another example, if you look at the industrial IoT, there's an immense amount of data being generated. There's one estimate that's about 1 exabyte daily. That's 1,000 petabytes or 1,000,000 terabytes of data every day. There's 30 billion connected devices. And what are we getting out of that? What are we using from that? Right now, estimates are less than 1% of the unstructured data that's being generated from these devices, which can be anything from digital measurements to maintenance service reports being done by technicians in the field. And less than half of the structured data is currently being used. Of the companies that have invested in industrial IoT technology, around a quarter, less than 26%, are seeing any value here. So we know that we should be measuring this data, we know that we should be collecting it, but we don't quite know what to do with it. And why is it that we don't know what to do with it if we have made all of these advances in data science, neural networking, deep learning, and artificial intelligence? If we look at data-enabled cars, smart cars, we see this progression where things that are well established, like onboard diagnostics, has been mandatory in all US certified vehicles since 1996. And we also see driver comfort features as standard equipment on most vehicles. But where we are today is that things like telematics and advanced driver assistance systems are only available in the high-end vehicles on the road today. And the cool stuff, the next generation, the predictive maintenance, the self-driving cars, that's all currently in development. So this is all still work that is underway, and there's a ton of potential in this space to connect physical systems with data. And we should care about this because data can actually save the world. This photograph is from just a couple weeks ago in Chennai, where one of its main reservoirs is now completely dry. Climate change is real. It's not a talk from me if I'm not getting a little bit political. We can't afford to wait for generational improvements to our technology to do things to make our world better, cleaner, safer. 1% efficiency across the board with gas turbines is the equivalent of millions of dollars in fuel annually, if not billions. Millions of tons of CO2 not going into the atmosphere. And that means it's the equivalent of millions of cars taken off the road permanently. We need to be able to do this. But the cycle time for getting 1% efficiency through traditional engineering means is anywhere from 18 to 120 months. So it can take 10 years to get 1% fuel efficiency out of jet engines, in particular, gas turbines, in particular jet engines which have heat and weight requirements to be mounted on aircraft. So how do we actually get to this point? How do we get to the point where we can use data to make our devices better, more efficient, safer, smarter, faster, more valuable? We want to think about data at various scales when we're thinking about the physical world. We want to think in terms of time scales from milliseconds to decades. But we also want to think about scales of how many units we have and how we're going to assess how data gets used in those units. So if we think about one unit being a single car, a single airplane, a single jet engine, we're using data anywhere from the millisecond scale, which is what we use in real-time control, to the decade scale for operational life cycle computations. So we look at what is the replacement time for major components in our vehicle. We look at things like operator feedback, which happens on the scale of not milliseconds, but seconds. So you might alert a driver to a road condition that could be hazardous, or a pilot, you might alert them to a low oil pressure in your jet engine. If you go out to the next level, at hundreds of units, this is what we might call the fleet level, where we see real-time in the fleet sense is monitoring on the order of minutes, roughly. So this could be things like tracking where your trucks are, either in the world or in a warehouse. It could be tracking your aircraft as they fly over the ocean using satellites and using communications between the aircraft and the satellite. And then you scale that up to things like service and offerings and product development at your business level, which happens on roughly year-long timescales, to fleet replacement and repurchasing, which could be at decades. And then when you get to, say, the hundreds of thousands of units or tens of thousands of units, now you're looking at product line scales. So you're probably not doing anything at the millisecond scale there, but you might be doing things as frequently as an hour, where you're doing telematics, where you're collecting data from devices that you have operating in the field, to see how they're performing, to see if they're up to your service level agreements. You might use that to plan recalls or maintenance scheduling. And you'll also want to use that to gain important feedback to engineer the next version of your product to make it better, smarter, and cheaper. So if we aggregate across time and if we aggregate over our units, we start to see that we have a multi-scale problem. Now, we're doing this currently. We're currently using data, generally speaking, in all of these different scales. But what we're not doing very well is connecting them. So how do we go from the millisecond scale on a single device, scale that all the way up to the entire life cycle of that device, and then all the way across a fleet and an entire product line. That's the central challenge of data science in the physical space. So to understand how to do this, this is where I'm going to shift to doing things a little bit more technically. We have to actually look backwards, not at the neural networks and the deep learning and all the cool stuff that's in TensorFlow and Keras now, but actually at the fundamental algorithms, because the smallest unit of what we're doing is at that millisecond, single unit, real-time scale. So let's talk briefly about dynamical systems modeling, and what is it that I mean when I talk about a dynamical system. A dynamical system is merely a system that changes with response to time. So here we have, we might call this a black box model, but it's not always a black box. It could be a gray box or a white box. But what we have is this sort of central model that we sometimes call the plant. This records our state, X, and as it changes over time in response to an input, U. We might call the operator A plant matrix, and the operator B a control matrix. And if these things are linear, we'll just call this a linear time invariant system, which is the simplest atomic unit of a dynamical system that you can create. Easy ways of thinking about this, the suspension system on your car is an LTI system, kind of-ish. Or you could think about throwing a ball that will follow dynamics that you can write in a state space form. This is the most basic process that we have. But we can, if we want to understand how we can use data to affect a process, we might want to start talking about feedback loops. So the simplest feedback loop is just simply to measure the state, think about where we want to be, compare those two, and use that to update our system. So if we want to, say, take an elevator from the ground floor to the 8th floor, our reference signal is 8, and we measure the state of where we are over time, and then we want to stop, ideally, when we get to 8 and not have the elevator throw us off the roof, or stop at the 7.5th floor. So this is a basic feedback control system. And these aren't very effective if you're just going to do it like that. But it's good because one bit of good news, rather, is that you can extend this very easily in something that's called a PID controller. And I promise that there's a data science angle to all of this, but I'll explain the PID controller because it is super fundamental and still used everywhere, including in the elevators in this building. A PID controller is a feedback controller, and it does three things. It computes a proportional term, that's the P, which is just a scaling of that error term. So if you tell it, the elevator, to go up to the 8th floor, and you measure what floor you're on, and you multiply that by some constant factor, that's your proportional term. The I is your integral term. So if you, at every time step, compute what the error is, and you add that all up over time, and you multiply that by a factor, that's your integral term for I. And then your derivative term is the rate of change at which you're approaching your actual target. So ideally, you don't want to have an elevator that just takes off as fast as it can go, and then slams the brakes when it gets to the 8th floor. You want something that starts off nice and gently, and then goes up very fast, and then slows down nice and gently as it gets to your destination. Why? Because you want to get there as quickly as you can, but you don't want the experience to be uncomfortable. A PID controller is able to accomplish that by using various scaling factors, which are called gains. The gains are essentially then multiplied by each of these terms. Those terms are added together to create a weighted sum, which is then used to feed in as the command vector for our plant system. So that's basically how a PID system works. But if you think about it, what other things are we familiar with where we choose weights to minimize an error? This is all data science is. If a data scientist starts talking to you about, Keras and neural nets and hidden layers and things like that, all they're doing is like painting really fancy language over the fact that all we want to do is compute weights that minimize an error. So the PID controller is a prototype of any sort of data science modeling approach. So we can actually see what this looks like in reality. So let's say that we have like a little drone that we want to use to take pictures of the audience here. And let's say that what I want to do is I want to start at 0 meters. I want it to take off and hover at 1 meter for 10 seconds, and then I want it to climb up to 1.5 meters, and then hover there for the rest of eternity. So we can do that, and I can write a PID controller, and I can choose a bunch of different weights. And so for any set of 3 weights, I could get lots of different responses. The blue, it overshoots slightly and then resettles. The green, it sort of has like this undershoot trajectory that eventually overshoots. And the red is just way too aggressive. It's like oscillating before it settles. So this is typical behavior of a PID control. And we can play with that, and we can optimize those weights to get the desired performance that we want. And what's great about the PID controller is if we want to build a more complicated system out of it, we don't have to do anything. It's very simple. In fact, it's so simple that I can fit all of the entire code for a PID controller on a single slide. And the last time I gave this talk, I actually live coded this. It's that easy. The challenge here is that the real world doesn't look like this. The real world looks like this, where we have noise and we have lots of factors that confound things. It's not always easy to measure. We were talking about rockets earlier, so here's an example problem. It's very important to know what the exhaust temperature of a rocket plume is, because that tells you what the efficiency or the power of your rocket engine's output is. So how would you measure the temperature of a rocket plume? You can't like stick a thermometer in there. It'll melt away. So how do we do that? Well, we need to be able to infer that measurement using some sort of statistical mathematical technique. And so in addition to the sort of real-time controllers, we've built something called a Kalman filter. Now, Kalman filter was invented by a guy by the name of Kalman. And this was really first discovered and used for the Apollo spacecraft. And there's lots of equations here. You don't have to understand them. They're really just there to try to like impress you. Because it's really hard to measure where a spacecraft is in translunar trajectory. And it's also very important to get it right, because you don't want to crash into the moon. That's a very difficult state to recover from. What the Kalman filter does is actually pretty simple. It uses the model, the plant model that we have, to make an estimate of its state at a time step, to predict where it's going to be at the next time step. We use some fancy statistics with things that are, we throw the term covariance around a lot. In particular, we think about process noise and measurement noise. So there's 2 different types of noise. One is if you have a sensor, the sensor could give you noisy readings, but your process can also have things like vibrations and things like that. So you have to account for them separately, but you factor in these noise characteristics, and then you have this sort of probability. So if you're measuring where a spacecraft is, and a spacecraft is very small in relation to the moon, and you're using radio measurements, you're going to have some sort of noise associated with that. So you need to use probability theory to filter out where it actually is. So if you do all of this fancy linear algebra, then what you get is a state estimate update. And then you have a posterior covariance and a posterior residual that you're then going to use in the next step. And so what this actually looks like if you diagram it out is something like this, where you have observations at each time step. Those observations are built on your plant models and your understanding of the process covariances. And then you have this hidden layer, which is your probabilistic output. Okay, so last slide, lots of equations. This slide, lots of arrows and things. And this is all very intimidating. But we can actually simplify it, because if you take any data science course, you'll learn about a hidden Markov model. And that's all that this is. A Kalman filter is just a hidden Markov model that works in a world where each state is dependent on the previous with some known physics. So what we have is our control theory world is the foundation of the algorithms that we use in the data science world. This is also true for things like backpropagation, which was invented because the backpropagation algorithm that we would use to train, say, a deep learning convolutional neural network was actually invented because to solve linear quadratic control problems. And it turns out the backpropagation algorithm is also the same algorithm that's used in automatic differentiation. So if you have a very complex piece of software and you need to understand its rate change with response to some inputs, it's literally the same thing as training a neural network. That's all it is. That's not to say that it's simple, but what it is to say is that control theory is actually in all of the applications that we develop, and we don't even realize it. So if you build a system that monitors your infrastructure and you install some observability tools, and you have things that trigger based on certain states, such as notifications that go to your infrastructure team, or alerts that might warn you of some behavior, or if you spin up additional instances using Kubernetes or something like that, you're actually creating these feedback loops. Predictive maintenance. If you want to do predictive maintenance for some machinery or something like that, components wear. You need to understand how those components wear and what the physics are. Even if you don't understand it perfectly, we can apply systems identification techniques to infer that model, and then to give those predictions, to also use those techniques to do some intelligent data science. So what this boils down to is that data science and physical computing are actually very closely related, and they have been for a very long time. We're starting to realize this now as we start building IoT technology and going, uh-oh, we've collected all of this data, what do we do with it? The algorithms that we need to use are actually really well understood. That's never been the challenge. The challenge has always been having the technology to implement them at scale. Also to have the data to do that. 30 years ago, we didn't have the ability to record exabytes or petabytes or terabytes of data. We can do that very easily now, and we can store it very cheaply. The business value is super clear. We know that if we can operate on our data, we can get value out of it. And the tools that we have never been better. So we could take the neural networking tools and adapt them to real-time or time series problems in a way that we've been doing in the systems identification world for almost 30 years. So we have this ability to couple these fields. So I'll wrap things up at this point, and we'll take some questions. But I want to wrap up with a quote from Colin McCarthy, who's, I think he's with AWS now. He gave a talk at QCon just a week or so ago, and he had this wonderful slide, because I'm not the only person who is sort of rediscovering control theory in the tech world. And his slide basically said that the fruit of control theory is so low that it's practically touching the ground. There's a ton of opportunity for us to learn from these deeply mathematical, possibly obscure techniques to build our systems to make them smarter. We don't actually need to reinvent anything. It's already there. We just have to be willing to embrace the problem and to talk to the people who are experts in those domains, to listen to them, and to use their knowledge. So thank you very much. My name is Emily Gorcenski again, and I'll open it up for any questions.